Welcome to the SEI podcast series, a production of Carnegie Mellon University's Software Engineering Institute. The SEI is a federally funded research and development center sponsored by the U.S. Department of Defense and operated by Carnegie Mellon University. Today's podcast is available on the SEI website at www.sei.cmu.edu/podcasts. My name is Suzanne Miller. I'm a principal researcher here at the SEI. Today, I'm pleased to have, again, Dr. Julien Delange, one of our researchers in architecture analysis and design language, among other wonderful things. And today, he's here to talk to us about security modeling tools, very important in our environment today. So, Julien, I wanted you to start by telling us sort of how did you come to be here and working in this area in security modeling?
So first of all, thanks a lot for having me today. So security, there is a lot of attention about security, and we have seen a lot of bad things happening. I think one of the highlights was last year with when Miller and Valasek were able to take control of a car from their couch.
That was very scary.
Another thing is we start to see a lot of issues with the medical domain and medical device. And I think people just start to be a little bit scared about that and start to wonder about what's going on. And it's a big impact for the company reputation.
Yes.
So when somebody discloses a vulnerability, consumer will no longer buy the product, or they're really scared, or they're worried about.
They certainly will worry about it, even if they still buy it. So what brought you, what is your background that led to working in this area?
So my PhD was about safety and security, so I was familiar with the topic. So when I started to see that there was a lot of attention about these topics, I started to think about developing new tools and methodologies, and especially applying that for the ADL language, basically the language we are developing here at Carnegie Mellon. And I think it was appropriate to care about all the different issues you can have in your architecture. So if you look back, most of the work that try to address security issue, these work care about mostly about software issue, like for example, you have buffer overflows, you have issue with resource allocation, concurrency mechanism, this type of thing.
Vulnerabilities that are in the software itself.
Exactly. But there is a lot of problem in the architecture, how you organize your resources, how you share resources among, for example, different tasks and processes. This is really important, and in fact, you don't have a lot of research on this. So we started to look at what is available and what are the approach. So in the UML and SysML community, there was some work that is, they are still working on it. For ADL, there was nothing. Beyond that, there is really few modeling tools.
Okay.
And I think this is really something important to have tools so that engineers can start to model your system.
Before you make commitments to a particular approach.
That's correct. So, it's not that there is no tools, but there are really a few, and they are not really user-friendly. And we wanted to make a tool that is more user-friendly and people can use the tool. So we started to develop these tools a year ago, and see how you can represent vulnerabilities, how you can see propagation of a fault. So if, for example, in your car, somebody can take control of the radio, maybe that's not a big deal. Maybe, they can change the music, and basically, they can bug you and play Shakira, but it's not a major threat, depending on how you feel about it. But they cannot take control of your car. So, for example, see how a vulnerability can reach your architecture, control your car or not. It's important. 1 or 2 years ago, I'm sure you've seen the news. There was a researcher that say he was able to take control of a plane from the entertainment system. And when he landed, unfortunately, the FBI was there to arrest him. So, I mean, there is still the question, it's possible to do that or not? And with this kind of tool, you can see the impact of the vulnerability and see finally if somebody can break in from the entertainment system. I mean, I think that everybody that fly today is interested by...
So the idea is that these kinds of tools are things that can make it easier for me to accept that risk as a consumer. But I mean, there's the consumer of the flying, but we've also got risks related to the medical devices, as you said. And it is very scary to think about, you know, an automobile, which we have trusted as being sort of this entity that is invulnerable, except to things like flat tires. But, you know, it's invulnerable to security issues like we have in our computers, but that's just really not true anymore. So how do these models make those vulnerabilities more visible to architects and to people that are interested in verifying security?
So we have different layers. The first thing we started is to work on just a flat model. That is, what by flat models I mean, it's you have to manually insert the vulnerability. You have to say, I have a car and I have, for example, a radio with a Bluetooth connection, and then somebody can control the car from the Bluetooth. So you have to explicitly put this vulnerability. But ultimately, this is not what we want. Ultimately, what we want is to automate the production of this model.
Right.
So I have a piece of software, and then from this piece of software or a model, I can generate this model. And then I see what are the vulnerabilities, which is what I will call the attack surface.
The attack surface, yes.
So all different vulnerabilities I have, and then I can analyze the connection between the different components and see the attack impact.
Okay.
And it's exactly what we've done in the safety community. If you talk about failure mode and effect analysis, I mean, all these different methodologies. The thing is, for security, we just start to look at it. So basically, the tool, you present the different vulnerabilities and the components, but we have a bridge to create that model from an AADL model.
Okay.
So just to give two examples, if you have two tasks in your AADL model to process and they access data, a shared data, and basically there is no concurrency mechanism that is, you know, used, then in that case you might have a security issue because the data is not correctly managed or protected.
Okay.
Another way is, for example, when you have different process.
So the AADL model itself will not tell you that, hey, Julien, you have a problem because you can get to the both of these tasks can get to this data without telling the other that they're getting to the data.
I mean, so the ADL model will contain the information, but you will not see it.
Right.
And then this analysis tell you this, but also the analysis tell you you have a vulnerability, first of all, and the second thing it will tell you is this vulnerability propagates in the architecture and how it can impact the other part of the system.
And that's something you can't do without a model like AADL, because that's the model that gives you the insight into the architecture of the system. So you need both pieces. You need something that models the architecture in a robust way so that you can see what all the connections are. And then you need something that's specialized to look for and analyze what are the vulnerabilities that are possible and that are actually present in this architecture. Is that correct?
Yeah, that's correct. I mean, another really simple vulnerability is, for example, you exchange data, and you exchange data that is critical without an encryption. Then you have different kind of vulnerability you can have. Basically, an attack called mine the middle. Somebody, you know,
mine the middle. Okay.
Either the guy can sniff the data, modify the data. I mean, there is many different attacks you can have.
Right.
So when you have such a model, we'll produce this vulnerability modeling, model, and basically we'll generate it, and the user will be able to see the different vulnerabilities and their impact. I think this is really what we want to do, is to show the impact. For example, I'm in my seat during my flight. Can I take control of the plane? I mean, can I basically use a vulnerability from the entertainment system and can it propagate to the
navigation.
Exactly.
Yeah. So what have you tested this kind of modeling? What kind of problems have you tested this on, or what kind of AADL models have you used this with?
So we apply this technique to two main domains, critical systems. The first is automotive, because there is a lot of attention. I think we are coming to an era when we talk about self-driving car.
And we live in Pittsburgh, and Uber is actually testing self-driving cars in parts of our neighborhood. So we have a vested interest in this.
Oh yeah, definitely. And it's not only, only Uber. You look at Tesla. I think that there is a lot of attention on this. Toyota. Everybody.
Sure.
And what is really interesting with the automotive domain is that there is not so much regulation. The regulations are not as well defined as in the avionics domain.
Sure.
We just start to work on this.
Yes.
There is a lot of efforts. Google, for example, they have self-driving cars since a really long time. Uber, they just started.
Yeah.
Many people here at Carnegie Mellon are working on this topic. For example, I really think about Dr. Phil Koopman, that investigate the unexpected acceleration issue with the Toyota Camry. He writes a lot about self-driving car,
right.
How you can make sure they're safe.
And one of the things I know is part of this, and I don't know how this has been addressed yet, if it has yet been in your tool, is that automotive, for example, there's quite a deep supply chain.
Oh, yeah.
You've got the manufacturer, and then you've got the people that provide the brakes, and the people that provide the brake pads, and the people that provide the sensors for the brakes. You can go 3 or 4 tiers down, and those are all different companies, and they all have different approaches to implementing things for different manufacturers. So the bringing together all of those potential actors into the model has got to be pretty complex.
Oh, definitely.
And is that something that you're able to do with these? Allow for multiple supply chain members to provide information, so you can have some information about what is actually happening in terms of the implementation?
Yeah. Remember that we started to work on ADL for the avionics domain, the avionics community, and the plane is exactly.
Multi-tier, very deep.
Exactly. So yeah, definitely you can apply this with ADL. You can use ADL to show the different tiers and how you decompose your system. So to come back to the previous question, we apply that for the automotive domain and obviously for the avionics domain. So in last year, we decided to work also with a SAVI group. That is, a big. SAVI is a big project.
Right. It's a consortium of airplane manufacturers that are trying to improve safety.
So we have, companies like Boeing, Rockwell Collins, Honeywell, and so on. And so we apply this technique, and we apply this technique to look at 2 issues. One is the issue with the entertainment system. Can you take control of a plane for your entertainment system? So we analyze this technique to try to have a sense about how the vulnerability can propagate and what it takes to basically compromise the system.
And then what it takes to protect from that compromise.
Correct. The second thing we analyze is the impact of the ADSB protocol. So ADSB is a protocol that basically is used to communicate between ground station and planes.
Okay.
And you have no encryption for that protocol. So there is some issue, like for example, you can inject plane to a ground station, you can inject plane on the plane. And it's kind of an interesting issue because if you think about it, for example, you can inject a plane in a plane, so the pilot can see a lot of planes coming.
So you can give false positives as well as other kinds of
and you can
false information.
And you can put stress on the pilot. And of course, the pilot will say there is no plane coming, so it's not true. But what about autopilot? What the computer will think?
Right.
This is something, maybe for an airplane it will not happen, but what about if we use the same technology for self-driving cars? It might be way more easy to do that. And to say there is for example, imagine you have a self-driving car, and then you tell to the self-driving car there is somebody that is coming in front of you, turn right. And what you have is you have somebody in the street, on the sidewalk, on the right.
Yeah.
So what are you doing? So this kind of problem, you can explore that. And this is what we want.
And you explore it within a model, not on the street. So that's important.
Well, no, yeah. We try to avoid this kind of test.
Yeah. So one of the things that this brings into my mind, which is not necessarily related to this exactly, but has there been any work done to take the standards for security and safety that are present in the avionics world and analyze them to say which of these really should be applied to automotive on the ground? Is that something that is relevant to this work, or is it something that you know is being done?
We are not doing this as part of this project because it's not in the scope of the project. But there is two things that are. I mean, if you are, I feel that you are scared about cars right now.
Yeah.
So for self-driving car, there is really a lot of efforts underway to standardize what needs to be done and verified for self-driving cars. So you have different levels of autonomy.
Right.
So, for example, you probably know that Tesla, the Tesla is not a full self-driving car.
Right.
It's an assistance.
Assisted driving, yeah.
Exactly. And ultimately what we want is self-driving car.
Although in speaking to some other researchers, I think a lot of us kind of are of the opinion that self-driving cars are probably not going to be a complete solution until no humans are driving cars, because we always inject variability into the algorithms in a way that is very difficult for the poor computers to deal with.
Probably. I mean, I don't trust myself when I'm driving a car, so...
Case in point! So there you go.
So the other thing we are doing is to see the impact, I mean, the trade-off between security and safety. So in fact...
Security and safety, okay.
So,
you would think that those were pretty compatible.
Yeah, and basically some people argue that it's the same thing. Some people say it's totally different. For example, if you take the example of the self-driving car, there is, what are we talking about? Are we talking about the security of the driver or the safety of the driver? And I think both concepts can overlap.
Yeah.
So this is why we are trying to see if they overlap, how they overlap, what is the impact of one on the other. So
yeah, I mean we know there are parallels, but there's also the difference between safety and security in my mind that informs this work is that idea of an attack surface and intentional. A lot of things that happen in safety vulnerabilities are accidental, and many of the things in security vulnerabilities are trying to prevent intentional attacks. So there's that difference. I don't know if that's really relevant when you get to the modeling, but it may be relevant in terms of how you prioritize the kinds of factors that you're looking at.
I have a funny example. You are on your car and you have an accident and your car flips and you're on the roof. What's going to happen? The door automatically opens, right? So it's for your safety. Right now, think about somebody jump on your car, the door's open, and he can steal your car. You see the thing?
There are some propagations that lead from one to the other.
And this is what we want to investigate.
Yeah.
So this is what we are trying to do right now.
So system architects that are thinking about this, that are trying to improve the security and safety of their systems and who are using modeling as a way of improving that already. Where should they go to get these tools and to get more information about your project?
So a policy we have in our group is to release everything as under an open source license.
Okay.
So all the tools are available on our GitHub space. So at SCI we have a GitHub area.
And it's a very rich GitHub space. There's your tools and there are lots of other tools there too.
So the tools are called AASPE. So you go on the SCI GitHub website and it's called AASPE. But I understand, I mean, it's just the source code. And for some people, they just want to use a tool and, start to use it in 10 minutes. So for that, we have an IT build, and every night we are building the tools again.
Okay.
And it's available in Osate, so you can download the Osate.
Okay, Osate, which is also where there are other AADL tools, and you can learn how to use AADL.
So you download the Osate modeling platform, and then you have to install what we call the experimental tools, which is right now, I mean, it's obvious, it's a research project. It's not stable, so we release that under an experimental feature. Install it, and then you're free.
Try it and give Julien feedback when you find things that you think need to be changed.
Exactly. Also, if people want to try it, last month I made a tutorial at Embedded System Week. So it was a full 4-hour tutorial that covered ADL modeling, safety modeling, and security modeling. And in fact, you can find the tutorial easily on something, the GitHub website. You put Embedded System Week Security Safety. We have slides. We have instructions that explain how you download the tool and use the tool. And we have models to use. Okay. So people can, they don't have to know ADL, they don't have to know all of this. They can just, see how it works, have slides. You have to click here and there, and that's it.
Excellent. So you're making it much more accessible to even people, and you're going to get people interested in ADL because once they see how cool the models are, they're going to want to do ADL, yeah?
Of course.
Okay. So I do want to thank you for joining us today and talking about this. I think this is, the more we can do in modeling, the less we have to do on the ground or in the air, and that really makes it safer for everyone, I think. So I'm really pleased to see this direction. You do have a blog post that is on this work, so that's another resource for our viewers. And those are available at insights.scI.cmu.edu. That's where all of our blog posts are. So I invite you to go there, find Julien's blog. His last name is spelled Delange, D-E-L-A-N-G-E. Not everyone has the French accent to go along with it, so I spell it out for them. We will include resources, the GitHub and other Osate resources we mentioned. Those will be included in this transcript. And the podcast itself will be available, as I said, at www.scI.cmu.edu/podcasts. It is also available on the Carnegie Mellon iTunes U site. Thank you all for watching, and thank you, Julien, for talking to us today.
Thank you.